Welcome to this video on solutions for density problems in physics. I will be solving problems from Physics by Halliday, Resnick, and Walker, 8th edition. It's my favorite physics book because of the way problems are designed to help you develop your skills in analysis and problem solving for the real world. At least that's from my experience. It's a very good book to prepare you for the higher levels of analytical courses in physics and engineering. For our first problem, we will be determining the density of the standard kilogram, which is a cylinder, 39 mm in height, 39 mm in diameter. So the key thing to solving this problem is to first determine the volume, and considering what has been given and considering that the radius is half the diameter d, we calculate the volume to be 4.66 times 10 to the minus 3 meters cubed. Density being given by the formula rho is equal to m over v, and considering that mass has been given at 1 kilogram, density has been calculated to be 2.15 times 10 to the 4 kilograms per meter cubed. Our next problem, we will be solving the density of the planet Saturn, given mass and its radius. We use the volume equation for a sphere in order to determine um, the volume of the planet given its radius, which we calculated to be 9.05 times 10 to the 21 meter cubed. Calculating density from this information, we get 6.23 times 10 to the 3 kilograms per meter cubed. For our third problem, we are tasked to determine the mass of a spherical shell described by its outer and inner radii. Using this, we derive the volume of the shell from the difference in volume between spheres, characteristic of the outer and the inner radii. So we have an outer sphere and an inner sphere. We get the difference of the two, and that is what we use to calculate the mass from the density equation. So the difference in volume is 20.6 cubic centimeters, and we get the mass as 184 grams. Problem 4 is quite similar to the previous problem, except that we are tasked to determine a solution that is symbolic. So we'll be using calculus in order to solve this. To solve this problem, we consider a differential volume element dV represented in spherical coordinates, given by the equation um, as shown in this slide. So after doing a triple integration and using the right limits, we get the volume of the spherical shell. If you notice, the only important um, variation or change in this hollow shell is really the radius. It, there's really nothing much in terms of um, the zenith angle or the azimuth angle. So by applying this to the density equation, we get the mass by multiplying the volume with the density rho.